Okay, I've got my trusty calculator in hand ready for this next one. We have a lot of work to do. This will probably take 2 videos, so let's get to this. What we are about to do is to determine what we call rate laws, and that is the equation that the rate is equal to K times the concentration. I'll put it down here. This is an example of one, but the rate is equal to K times the concentration of some substance we'll call A, the M power, times the concentration of B, the N power. This K is a constant that is going to equate the rate of reaction, which is measured again in moles per liter per second, with each of these concentrations to particular powers. Now the thing is, this doesn't get that complex, but you have to kind of follow the process here, so I'll try to break it down as much as I can for you. But these two exponents represent the order of reaction. We talked about that very early on in this chapter. So they are going to tend to be ones or twos, no more than 2. And it's possible to have like a square root or a half exponent, or even a 0, and that's more common than a half because there may be times in which one of these two reactions will have a 0 effect upon the rate. If it has 0 effect upon the rate, then the exponent is 0, which means it's going to be like, in this case, b to the 0 power, which is 1, and it will just drop out. But we have to figure out experimentally what it is. So we run a series of experiments that's going to get us to that point. We look at the data, and we use the data to figure out these exponents out. And once we figure out the rate and these two exponents right here for your concentrations, we then solve for K. And we'll talk about the label K. Now remember, labels of constants are basically nonsense, except for when we're doing graphs of certain scientific laws in which the rate now becomes very important, like the ideal gas law. What the heck is a liter atmosphere over a mole Kelvin? Well, a liter atmosphere over a mole Kelvin is just putting all the variables together in some form that is going to establish the pattern and which predict either P or V or N or T. So this is just for predictive powers, and so it's going to change with every order too. So I'm going to tell you up front that just because we get a particular label for K in one problem, we may get a different value or label for K in the other one. And these are very distinct with each equation. I have yet to see 2 reactions run where they have the identical K. I just can't imagine that ever happening. But we'll get to that. So here is the first problem. Now we're going to take a look at problem number 43 on page 641. We're going to do 43, 45, 47. And we're going to go through the process of each of these. Now, the equation here is, this is called azomethane. Azomethane is a fairly unstable gas, and when it breaks down, it forms ethane gas and nitrogen gas. And again, when we do rate laws, we look only at the reactant, we don't look at the products. And that means then that the equation, since this is the only reactant we have, is going to be R equals the concentration of that azomethane to the M power. Nothing else. So here's how that works. We start off, and this is done intentionally. This is not a coincidence that this is double this. They do that on purpose. They try to use values that come out evenly and hope that the rate changes as evenly in its change as well. Doesn't always, particularly when we do it in the lab. Things always get messy. But the nice thing about this is that they try not to make it too messy so that you can see the pattern, so that if you ever have to do a lab like this, you can at least have the process down and predict based upon the ugliness that you have. So let's do this. So like I said, as we go from here to here, we're going to double the concentration. Okay, so when we do that, this is going to give us the exponent of m when we see what happens here with the rate. Remember, the rate is equal to the constant times the change of concentration with the exponent. So that is our exponent right there. And when we look at the change of the rate right here, if you can't tell by looking at it, and you probably can, but if you can't tell by looking at it, you divide this one at the head of the arrow divided by the beginning of the arrow. So the division is going to go in reverse. So in other words, it's going to be 5.6 times 10 to the negative 6 moles per liter over 2.8 times 10 to the negative 6 moles per liter. Moles per liter cancel out. And you punch that out in your calculator, and you get 2. So what that means is that this 2 is going to equal to, now we're going to take this exponent right here, and we're going to move it right over there, because we want to see how this affects this change in rate. So this becomes 2, I'll scratch that out so it doesn't get confusing, but I'll just emphasize the fact that this is actually involved here. This is actually 2 to the first power. And since we have here m is 2 to the m is equal to 2 here, this is our 2 to the m equals the change in rate 2. And we get then m is equal to 1. So we start with the m here. And actually, I should have covered this whole thing right here. Bring that whole thing over here and make that 2 to the m and set that equal to the change in rate. Change in rate goes right there. So 2 to the m power equals 2, that change in rate that we got when we divided. So this is the change in rate right here. Actually, delta is not a good way to put it because we didn't subtract, we divided by. So I'll put kind of change in rate. So it isn't a true subtraction, it's a division. But regardless, the exponent is 1. So that means then that this is going to equal to 1 for the exponent. Now, that becomes real important. Now we can predict what the value of k is, and the k is going to be the same throughout any kind of change in concentration and rate. We can predict based upon the value of k here. So, what we're going to do at this point is we're going to pick one of the 2 experiments and plug in the numbers we have for that. So, I usually go with the first one, and I'm going to use the first one for my R, my first R. And I, by the way, means the initial rate. We're looking at what was the rate of reaction at the very beginning of the reaction, and this I here means we're looking at the concentration at the beginning, and then from that is where we're going to come up with this equation. We know that other time frames will give us values that we predict later on down the road, which is another lesson. So we're just dealing with the initial rate and concentration. So the rate here we said for number 1 is 2.8, and that should be liters, moles per liter per second. Per second. Like that. Okay, because it's a rate. It's not just moles per liter, that's concentration. This is a concentration here. That's the rate, moles per liter per second. 2.8 times 10 to the negative 6. So we have 2.8 times 10 to the negative 6 moles per liter per second is equal to K, which we don't know is what we're going to solve for, times the concentration in number 1. So initial concentration number 1, 1.13 times 10 to the negative 2. And that is moles per liter. And it's really important to include the labels in these equations so that you can see how K's label is going to be determined. So now, we're going to divide both sides by 1.13 times 10 to the negative 2 moles per liter. You see the moles per liter are going to cancel out here. So on our calculators, we're going to take 2.8 E negative 6 divided by 1.13 E negative 2, and that gives us let me try again. My calculator is being goofy here. Let me try another calculator. No, that's not right. 2.8 E negative 6 divided by 1.13 E negative 2, and I get 2.48 times 10 to the negative 4 equals K. This cancels out. Now, I have not ignored this label here. I want to come back to this though. I just want to make one point on some given figures. Technically, the answer should have 2 sig figs in it because of 2.8, but as a matter of consistency, as I've always done in Chem 1, I'm going to continue with Chem 2, I'm going to ask for 3 sig figs in every, just for consistency's sake. Now, you notice here that we have the moles per liter cancel out, and that leaves us seconds in the denominator. So a lot of times you see it written like that, 2.84 times 10 to the negative 4 per second equals K. And you may go, what the heck does that mean? And I'm going to tell you, it means it's a constant. It's not supposed to mean anything. It's just binding the two sides together. Now, another way of writing this, and this is the way I prefer it, you can use either way. I don't much care. But it's 2.48 times 10 to the negative 4 seconds to the negative 1 equals K. Remember, if it's a reverse or an inverse, it is the negative exponent. And since the exponent here is 1, that becomes negative 1. So either one of these two answers is acceptable for a value of K. So, we see that this is a first order reaction because the exponents add up to 1, because there's only 1. And we see that the label for a first order reaction is seconds to the negative 1. Keep that in mind. Okay, so we go on to the next problem.